Welcome back, class. So we are starting our new chapter, which is actually sampling of continuous time signal. So far we have learned about the discrete time signals, properties of discrete time signals, and characterization of the discrete time signals and LTI systems using discrete time Fourier transform and Z transform techniques. So basically in this chapter we are going to learn about the techniques for the generation of discrete time signals from continuous time signals. So actually naturally we have continuous time signals. Okay, so in the earlier chapter in the start we have learned that there are different kind of signals. For example, this is a continuous time signal. And now if you want to convert this continuous time signal to a discrete time signal, okay, so then how we can convert this thing? Basically how this thing happen in actual scenarios, in actual applications. So that is the focus of this chapter. So this process basically that we can convert a continuous time to a discrete time signal. Okay, the technique which is used for this is called sampling. So this complete chapter is about sampling, that how we can do this process. What are the different constraints of this process? What is the procedure of this process? Okay, so we will learn about the sampling, issues in sampling, discrete time processing, and reconstruction of the signal from the discrete time. Okay, so basically first we are converting from continuous to discrete, okay, or from analog to digital. Okay, first we will learn this thing, and then we will also learn that how we can convert from digital to analog. Okay, that will be basically reconstruction. So we will learn about this whole things in this chapter. So before going into the details, okay, a quick review of the impulse properties, that when an impulse multiplied with a signal, so we will get the signal value at the impulse location, right, with that impulse. Okay, and the summation of the impulse is always 1. Okay, and the third property, which is actually also called a shifting property, that you are multiplying a signal with an impulse, and now you are also taking summation or integrating. Okay, so we know that this will be equal to x of n minus m and impulse. Okay, and summation of impulse is 1, so we will get only function value. Okay, so when we actually multiply a signal with an impulse, we will get the function value at the impulse location, or signal value at the impulse location plus that impulse. So but if we integrate that, okay, we will get only the signal value at that impulse location with no impulse. Okay, so these are just some properties which are actually very important for the understanding of the different concepts of this chapter. So the first topic is periodic sampling. Periodic sampling is you have a continuous time signal, okay, a periodic signal. Okay, so you are using a continuous to digital converter. Okay, continuous to discrete time or digital. Okay, digital or discrete. Okay, C to D converter. Okay, so if you have a continuous time signal, okay, for example this is my continuous time signal. Okay, now as we learned in the first chapter, if we take the samples of this signal, for example at this location, at this location, at this location, at this location, okay, if you take the samples of this continuous time signal, this is my continuous time signal. Now if I take the samples, okay, at different time intervals, okay, for example this is t, this is 2t, this is 3t, okay, that is the sampling period. Okay, or inverse of t, that will be the sampling frequency. Okay, so by taking the samples of continuous time signal, we can convert that signal to the discrete time. Okay, and this is the general description of that thing. So basically what will happen, okay, we can represent a discrete time signal, okay, as the sampled version of the continuous time signal. Okay, that we have a continuous time signal, and if we take its different samples, okay, depending on the sampling frequency, that will give us a discrete time signal. Okay, so this is the mathematical representation of the this continuous to discrete time conversion. Okay, so basically how we can achieve this thing. So if you have a continuous time signal, okay, and if you want to for example, this is our continuous time signal, and if you want to get these samples points, so we can get that by multiplying this signal with an impulse train. Okay, so basically this is one impulse, this is another impulse, shifted impulse, this is another impulse, and so on. Okay, so if you multiply this continuous time signal, okay, with an impulse train, okay, with an impulse train, okay, so we can get the function value at that impulse location, right? We can get the function value at that impulse locations, okay, with that impulse, and then if finally integrate, we can get the discrete time signal. Okay, so basically when this signal, continuous time signal, is multiplied with this impulse, okay, multiply with this impulse train, okay, so whenever two signals are multiplied, that process is also called as modulation. Okay, so basically this is a kind of a modulation. So what is our impulse train? Our impulse train is shifted impulse. Okay, and you are multiplying these two signals. Okay, now what is actually happening here? Okay, so this is t, this is also t. Basically this signal is being multiplied with an impulse. So by applying the shift impulse properties, what will happen? We will get the function value at the impulse location, right? And what is impulse location? N times capital T. Okay, by using the impulse property, so we will get this thing. Okay, so that is basically our discrete time signal. Okay, so this picture actually shows that if I have a continuous time signal and this is my impulse train with a sample period of t, okay, so here I am taking more samples. Okay, so this is the same signal, but here I am using a different sampling frequency. Okay, here I am using a low sampling frequency. Okay, here I am using a high sampling frequency. Okay, high sampling frequency means time period is short, so I am taking more samples. Here I am taking less samples. Okay, and eventually what will happen, if I integrate, I will get only the function value at the impulse location. Okay, that is basically my discrete time signal. Okay, which is actually the sampled version of the continuous time signal. Okay, so this is just the illustration of the concept of sampling. So this is just the same formula which I have described earlier. So whenever we multiply a function with an impulse, finally we will integrate, so we will get the only this thing. Okay, now if we talk about the frequency domain analysis, okay, so we can do that very easily. Okay, so for example, we know that our sampling function is this impulse train. Okay, so if we take its Fourier transform, okay, we know that if we have an impulse train in time domain, if we take its continuous time Fourier transform, we will get the impulse train in frequency domain also. Okay, with a multiplier of 2 pi over t. Okay, so this is the Fourier transform of the simple impulse train. And if we have a continuous time signal, if we take its Fourier transform, we will get xc of omega. Okay, so these are the Fourier transform of this continuous time signal, and this is the impulse. So here basically if we define the sampling frequency, okay, so sampling frequencies basically here s is coming, so we're getting a impulse train at the different sampling frequencies. So omega s is basically called the sampling rate, sampling frequency in radian per second. Okay, this is 2 pi over t. Okay, 2 pi f. Okay, just for the discrete time we are representing using small omega here. Okay, so this is called sampling frequency, and so basically the two signals, okay, if they are multiplying, okay, in time domain, okay, like we multiply the continuous time signal with the impulse train. So if they are multiplying in time domain, so if we take their Fourier transform, okay, so their Fourier transform, they will be convolving in frequency domain. Okay, so the Fourier transform of the continuous time signal, it will be convolving with the Fourier transform of the impulse train. Okay, and when the convolution happens, basically this is what, this is just an impulse train. Okay, so when this function convolve with this one, what will happen? We will get this function value at the all the impulse locations. Okay, so finally we will get this thing. Okay, first this is omega, so it will be replaced with the impulse values. So basically, for example, if we have one one function, then we are getting its periodic versions, okay, at different impulse locations, okay, like in time domain. So we will see the relevant examples and the other stuff, okay, relevant to the sampling, okay, and more details about the sampling in the live session. Thank you very much for your time.